Hello, everyone, and welcome back to our statistics lecture series for ENIGMA-U. Today, we are going to be expanding on the topic of hypothesis testing that we introduced in the last lecture. We're going to learn a new type of hypothesis testing, and then we're going to talk about what effect size and power are and why they are important variables to report in addition to our hypothesis testing. Every time, I'll do that every time. Okay, just as a review, we're going to go over what hypothesis testing is. Let me make this smaller so that you can see what we're talking about. So hypothesis testing, as a reminder, is a statistical method that uses sample data to evaluate a hypothesis about the bigger population. It is one of the most commonly used inferential procedures in statistics. And although the details of hypothesis testing differ from one situation to another, the general process and the underlying logic are going to remain constant. These steps are the ones that we talked about last lecture, where we state a hypothesis about our population. We are going to define a method that we will use to make a decision about the hypothesis. We obtain a random sample from our population, we collect data, and then we compare our collected data with our predicted hypotheses, and then we finally make a decision about our hypothesis. We're gonna today, as we did before, combine the topics of z-scores, probability, and the distribution of sample means. And as a good reminder, the general goal with hypothesis testing is to rule out chance due to sampling error as an explanation for the results from a research study. Say there's a treatment effect that is because of the treatment effect and not just because of sampling error. As another review, the one sample z-test was the hypothesis testing that we learned about in the last lecture. It was the most rudimentary, simple, I guess, hypothesis test, and it's going to be a good background for learning about null hypothesis significance testing, which is the new test we're learning about today. This one sample z-test, remember, we used a z-statistic to determine if the mean of a sample after treatment is different from the mean of the population before treatment. Those are the two things that we're comparing. We're going to go over this process with the understanding that the process for null hypothesis significance testing, the new test we're learning about today, is largely the same, just with some key differences. So, as a reminder, we make a hypothesis about the value of the mean after the treatment. The null hypothesis is that the treatment will have no effect, the means will be the same. And the alternative hypothesis is that the treatment will have an effect. The mean of the sample after treatment will not be equal to the mean of the population before treatment. The second step is we set a criteria for a decision, which is an alpha value. A common alpha value that we use is 0.05. We're going to get into today what an alpha value actually represents. But our understanding up until now is this alpha value is what we use to set our critical zone, the part on the outside of the distribution. The third step is we take our data from our sample and we compute the test statistic. That's going to be our z statistic right here. Remember, it's a comparison between the actual difference between the sample and hypothesis over the standard difference between the sample and hypothesis with no treatment effect. So essentially figuring out how much of the difference is due to chance. That's what our z statistic is saying. And then we compare our z statistic. We see if it falls in our critical zone. If the z statistic falls within our critical region on the outside, that means our p-value is less than 0.05 and we reject the null hypothesis, which means that the mean after the treatment is significantly different than the mean before the treatment. But if the z statistic falls outside the critical region in that middle section of our distribution, then we fail to reject the null hypothesis. The mean after the treatment is not significantly different to the mean before the treatment. Okay, here are just as another reminder, some factors that are going to influence the one sample z-test. Here's our z statistic. There are three factors that determine whether a z-score is going to be large enough to be in your critical zone. Looking at your numerator, the first factor is the difference between the sample and population means. As you have an increased difference between your mean and your sample mean and your population mean, your z-statistic increases. And then the second two factors both fall within the denominator, the standard error. When you have greater variability in the population before treatment, then that is going to decrease your z-statistic. And if you have an increased sample size, you're going to have a smaller standard error, and then you'll have a larger z-score. So greater variability decreases your z-statistic, greater sample size increases your z-statistic. Okay, and then these are the final thing we're going to go over with the one sample z-test is just some assumptions that we make. When you're doing this, when we justify that these assumptions have been met, then we can conclude that the hypothesis test produces a justified conclusion. So the assumptions that we make are, number one, that the dependent variable was measured on an interval or ratio scale, not nominal or ordinal, that random sampling was used and was selected from your population of interest. There was something called independent observations, which just means that the values in your sample consist of independent observations or observations that are independent of each other, which you're like, obviously, that's what the name states. But it just means that the occurrence of picking the first event doesn't affect the occurrence of the second event. So an example of this is measuring the height of a class of students. Measuring the height of one student does not affect the height of the second student that you measure. Those are independent observations. Then we have to make sure we have homogeneity of variance, which is just that the standard deviation of the sample is pretty much the same as the standard deviation of the population. And then we also have normality. Our dependent variable is going to follow the normal distribution. And based on the central limit theorem, we generally assume that if your sample size is more than 30, then your population distribution is going to be nearly equal to normal. Okay. Now, up until now, we've been talking about hypothesis tests where you have an alternative hypothesis that just expects change from the population mean. It doesn't assume a direction for that change. That's why we had the two tails in our distribution, the two critical zones, because we said the change could be positive or it could be negative. We don't know. We just know there's going to be a change. When a specific direction is expected for our treatment effect, if we expect the treatment to either change our mean positively or negatively, then it's possible for a researcher to perform a directional test, which we call the one-tailed hypothesis test instead of two. The difference here is that when we're stating our hypotheses, and the null is still just going to be that there's no effect. The alternative, however, is not just going to say there is an effect. The alternative hypothesis will say the mean is either going to increase or the mean will decrease. This is what a one-tailed hypothesis test is going to look like with your critical zone. Before, we had the two-tailed test. That means we had a critical zone on this side and a critical zone on this side, and we divided our alpha between the two tails. However, with a one-tailed hypothesis test, instead of dividing the 5% critical region between the two tails, a directional hypothesis test just postulates that the effect is going to be either positive or negative. So you put the entire 5% of your critical region on whichever end of the distribution you are hypothesizing about. So if your critical zone, your one tail, is on the positive side, then you say an effect is hypothesized to occur in the positive direction. And your mean is going to get bigger. If you put it on the negative side, you're hypothesizing that an effect is going to occur in the negative direction, or your mean will get smaller. Like we said here, this is what a two-tailed hypothesis test is. And the idea here is just that two-tailed hypothesis tests don't specify direction. The null hypothesis can be rejected if the sample mean lands in either of these directions. And a good point here is that, remember, your alpha level for a two-tailed has to be split between the two tails. So instead of just putting all 5% on one side, we put 0.025 on this side and 0.025 on that side. The major distinction, like we've said, is the criteria between a one-tailed and a two-tailed test is the criteria used for rejecting the null hypothesis. A one-tailed test is going to have a larger critical zone because all 5% is on one side. And so the difference between your sample and your population means can be smaller in order to reject the null hypothesis. You don't need as big of a difference because so long as the difference occurs in your specified direction. If it occurs in the other direction that you weren't anticipating, then you will get an error. A two-tailed test, though, because we're splitting our alpha level between two sides, the difference needs to be relatively large between your sample mean post-treatment and your population mean pre-treatment. But a two-tailed test covers either direction of change, which is nice. So with that in mind, let's talk about some uncertainty and errors that can occur in hypothesis testing. So hypothesis testing, like we've talked about, is an inferential process. So we use limited information about a sample to make a general conclusion about a bigger population. It's inferential, it's not exact, precise, right? Because that happens, there are a couple of errors that we can make. There are two specifically possible errors. The first is a type 1 error, or we call this an alpha, or alpha is the probability of this. A type 1 error is a false positive. So it's when we conclude that the treatment does have an effect, when in reality it does not. A type 2 error is the probability of a false negative, when we as the experimenter conclude that the treatment has no effect, but the treatment actually did. There are also two possible correct decisions. A correct rejection is a true negative when we decide that that no effect exists, and that's the truth, no effect exists. Or power, which is a true positive, where we decide that an effect does exist, and that is true, the effect does. Let's go a little bit more into each of these types of errors. Type 1 error, like we said, is a false positive. It's when a researcher rejects a null hypothesis that is actually true. We say that there is an effect when in reality there was none. This can happen sometimes when we as researchers obtain an extreme non-representative sample, when our sample mean is in the critical zone, but it's just because of sampling error, or it was just the random selection didn't serve us well. Fortunately, we structure our hypothesis tests to minimize the risk that we'll get a false positive, because a false positive is a pretty big deal. The alpha level here, the same alpha level that we talked about when we're determining the critical zone, is actually, the definition of alpha level is the probability that the test will lead to a type 1 error or a false positive. So if we have an alpha level of 0.05, what that means is that there is a 5% chance that we will get a type 1 error. Then the converse of that, 1 minus alpha, is the probability of a correct rejection, that the test will lead to a true negative. So this is a diagram that we'll be looking at and adding a little bit more to throughout this lecture, but let's just take a quick peek. This orange distribution represents the null hypothesis where no effect exists. And this is when that is true. This blue distribution represents the alternative hypothesis where the null hypothesis is false and an effect does exist. These axes, this black axis right here, on this side of the axis is when we fail to reject the null hypothesis. This side is when we reject the null hypothesis. So what you can see here, summarizing what we've learned about type 1 errors, when we fail to reject the null hypothesis and the null hypothesis is true, that's what this is called the 1 minus A. That's the correct rejection. However, when the null hypothesis is true, but we reject it anyways, that is a false positive, a type 1 error, and that's represented here by alpha. This brings us back why it is so important to select an appropriate alpha level when we're running a hypothesis test, because the alpha level is going to serve two functions. Number one, it's going to help us to determine the boundaries for our critical region by defining the concept of a very unlikely outcome. That is what we've talked about in the past lecture, right? But the new job of an alpha that we're talking about now is that it also helps determine the probability of a type 1 error. So our big job when we're setting an alpha level is to minimize the risk of a type 1 error. That's why alpha levels tend to be very, very small. By convention, what it says here, the largest permissible alpha value is 0.05%, a 5% chance of a type 1 error occurring. If you want to decrease the risk of a type 1 error, decrease your alpha level. Just put it at 0.01 or 1% or 0.001, 0.1%. But an important thing to remember is that as your alpha level is lowered, your hypothesis test is going to demand more evidence from your research results. You need a bigger difference between your sample mean post-treatment and your population mean pre-treatment in order to conclude that there was a treatment effect as your alpha gets smaller. Now let's move on to type 2 errors. So type 2 errors are a false negative. So this is when the researcher fails to reject a null hypothesis that is actually false. You're saying that there was no treatment effect when in reality there was. This often happens when, or another way to describe this is if your sample mean is not in your critical region, even though the treatment actually does have an effect on the sample. And this often happens when the effect of the treatment is relatively small, or yeah, that's actually just when the effect of the treatment is relatively small and we just miss it in our statistical testing. The beta level right here, beta, is the probability that the test will lead to a type 2 error. Just like alpha is the probability of a type 1, beta is the probability of a type 2. It's the probability of a type 2 error is going, to depend on a number of factors. So it's actually represented by a function, not just a specific number, and we're not going to get into that today. But in general, a type 2 error is not as serious as a type 1 error. So our beta is often higher than our alpha. The converse, like we talked about, 1 minus beta is the probability that a test is going to lead to a correct rejection of the false null hypothesis, saying there is an effect when there actually was, and that's called power, the probability that the test will identify a true treatment if one really exists. So adding this to our little diagram here, if our alternative hypothesis is true, our null is false, and we reject the null hypothesis, that's awesome. That's called 1 minus beta, that's power. But if our null hypothesis is actually false, if our alternative is true, but we fail to reject it, that's that type 2 error, the false negative, the beta. Okay, this right here are just two representations of those ideas combined. I find this really helpful. You can take a screenshot of this. This is just some really good summary diagrams. Here we've combined both parts of that diagram we've been talking about. We've just overlaid them one on top of the other. And here is just a really helpful chart that says this is what the experiment decides and this is reality. And then if you cross the two, which correct decision or error do you get? Something I'll point out about this diagram before we leave this slide is just that hypothesis tests are set up so that the probability of getting a type 1 error, a false positive, alpha, is minimized. What that means is when we minimize our alpha, our beta is going to get bigger. When our probability of getting a type 1 error decreases, the probability of getting a type 2 error increases. We'll talk a little bit more about those relationships in the next lecture, but that is just something to keep in mind to navigate or balance when you're setting up your testing parameters. Excuse me, just got an email. And then before we take a break and go to the next lecture, let's just talk about some of the limitations of null hypothesis significance testing. I really like this quote up here. We'll look at this paper in a second, but it says null hypothesis significance testing provides the illusion of certainty through supposedly objective binary accept or reject decisions that are based on practically not very useful p-values. And that basically summarizes this whole page. Let's go into some of these bullets really quick though. So one of the limitations specifically is that the focus of a hypothesis test is on your data, not on your hypothesis, which means that when the null hypothesis is rejected, we're making a strong probability statement, but it's about the sample data, not about our population hypothesis. In other words, it means that the alpha level is not identifying how likely it is that our hypothesis is true or false. It's telling us how likely we are to be making an error, right? That's what our alpha is. And more on that in a second. So the p-values, so our alpha also, don't give us any indication of the size of a treatment effect or about the precision of our estimates. They just, when we are using hypothesis testing, what we are doing is figuring out whether or not there is a treatment effect. We have no information about how big that treatment effect is, how precise our measures were, things like that. And that's a massive limitation. Like we talked about in this first bullet, null hypothesis significance testing results are also often commonly misinterpreted. The alpha values are not the probability that our null hypothesis is false, like we talked about before. It is the probability of committing a type 1 error, which is just different. And a lot of times people forget that little nuance when they're reporting their values. The big ticket item here is that null hypothesis testing was originally designed as a weak preliminary heuristic. It was not designed to be the only criterion by which we determine that something is a scientific fact or discovery. It was designed to be a preliminary test that we run to determine whether or not this hypothesis, this research question, merits further study. Should we put more time, more money, more effort into this question? If you get a treatment effect from a hypothesis test, then you can say, yes, let's start doing this more in depth. Let's do some more rigorous statistical testing, some more rigorous experiments. We should not be using it to determine whether or not something is a scientific discovery or fact. And because of this, if we're only reporting our null hypothesis significance test results, our p-values, that might foster selective reporting, subjectivity, and non-replicable false positive reports, all of which are not really good. So how do we avoid these results? This is that paper that this quote is from. This quote is from this paper in Frontiers in Human Neuroscience. It's called "When Null Hypothesis Significance Testing is Unsuitable for Research, a Reassessment." And I really like this first sentence here. Whenever researchers use null hypothesis significance testing, they should justify its use, first of all, and then we should publish pre-study power calculations and effect sizes, including our negative findings. And then hypothesis testing studies should be pre-registered, which we'll talk about in a bit, and optimally, our raw data should also be published. Yes, and we, in the next section, are going to talk about what power calculations and effect sizes are and why they are necessary to publish in conjunction with our null hypothesis testing results. Okay, so we're going to take a quick break, and then we're going to come back and talk about power and effect sizes.